Right. So when we talked about this yesterday, we said, should we do recorded demos? I said, no, let's do it live. So we're doing it live. All right, so I want to change topics a bit and go back to the model-driven conversation that we had earlier today. And we're going to show you another demo at the end. But before we get there, just to revisit sort of some of the core concepts that we heard about this morning and how do they apply to the network elements themselves. So first, we often talk, I find, about sort of the surface of the problem in terms of how you access data or how you transport data to and from network management systems or management applications. And really the way we're thinking in terms of the problem is it's really about the data and how you represent that data externally in a way that is structurally, syntactically, and semantically correct and consistent. Right? And that's why the models or the concept of a model is so important, because what I want to do to make the system usable by higher level software is to be able to expose these concepts, expose these structures in a way that's very easy for software to process. Now, this isn't the first swing that the networking industry has taken at models. And sometimes when we have these conversations, we go, well, how is that different from foo? Right? And for those of you who remember CMIP, I was but a child, so I don't. It was kind of an attempt, right? Define model hierarchy, extensibility, a simple set of operations that you could perform on it. So I think today we sort of collectively have an opportunity to make things better for the software that manages networks and sort of get networks up to the same level that we saw for servers and the rest of the infrastructure by really embracing and pushing model-driven APIs. And that's kind of why we're in it, right? What we hope to get out of it. So the concepts are within the system itself, we have a model. Applications access the model over an RPC mechanism. There is server-side tooling to be able to make this relatively pain-free, right? And he's talked about some of the examples that are published there today for Go and Python bindings, and fully expect more tooling to appear over time. And then there's how do I stuff the things onto the wire in a way that's relatively efficient, or at least pleasing to whatever philosophy that I have. And then how do I transport it back and forth to the network element, and how do I manage some of the core concepts of a network element, such as there is a config and I need to change the config and commit state to the config and potentially roll state back from the config. So nobody asked this morning why Yang, but I brought a slide anyway. And really Yang is just, it's a very convenient language to describe models, right? That's why we're going with it. And Yang was originally very tight. So this is a cookie cutter, and this is a cookie, right? So Yang describes the shape.
For clearing that up.
You're welcome. And then inside the shape, you have, in this case, netconf XML because they have common parentage. But you have whatever you put in the cookie cutter, right? That's sort of the way to think about it. But what we're doing from an implementation point of view is we want to have a broad support for models, and we believe that we're in a world where there are going to be multiple organizations and bodies that will produce normative models, right? And so the implementation needs to deal with that effectively and efficiently. Secondly, how do I get the model information to and from the device? And there again will be there'll be a number of encodings. Some of them will be usual suspect encodings. Some of them will be sort of interesting encodings that are relatively new to the networking space, but present a set of advantages that merit consideration. And then finally, how do I interact at a transport level with the device and have some basic RPC semantics, right? And here you're going to have, as you'd expect from the networking space, netconf and resconf, and also G Rpc, right? So the demo we're going to show you in a slide or two is going to involve using gRPC on a networking device to transport OpenConfig BGP, or to configure the device using OpenConfig BGP. But before we get there, a little word on the implementation. So if I slice the network device open, what do I see? And there was a question earlier today about, well, how much of a first-class citizen is the model when you implement it, right? Because at the end of the day, XR, just like other network systems, have an internal model representation which contains all the configuration and operational data, right? So this is the source of truth, and all the features that run on the system use that, right? Usually when you come in through the CLI, you're coming in the green path to whatever the internal state storage mechanism is. And what we believe is the right approach is you want to get your model representation as close to this as possible, and you want to be able to represent that state according to the set of models you're going to support. So our implementation will have a framework that takes model definitions that may be very close or identical to how we represent the functionality internally, sort of device-specific models. There will be models that we have for to adhere to IETF RFCs, and there'll be models that we have to, for example, implement OpenConfig specifications and ... vertically. Okay, and then you can access the model through whichever transport you're interested in, right? So I think the big thing for us when we've been working on this is to make sure that we have the tightest possible coupling between the way the external system wants to see and access the data through the form of the model, and how that data is implemented and how the information and state is maintained and managed in the system. All right, so extra offerings for the demo gods. So we're going to show you, I think this is the first public showing of gRPC and OpenConfig in action on iOS XR. The person doing it is, as I said earlier, in Washington, D.C. We were joking about using hotel Wi-Fi. It's an excellent facility. We're going to use hotel Wi-Fi here and hotel Wi-Fi on the other side. So it's going to be great.
All right, guys. So I'll give you a quick demonstration of model-driven programmability in iOS XR. I'm going to focus in particular on the OpenConfig BGP model. Let me show you the setup that we have. We have 3 routers, each of them with their own dedicated AES and one prefix that they advertise. And R2 and R3 have been pre-configured. R1 doesn't have any BGP configuration. What we're going to do from a host, we're going to be using both netconf and gRPC to configure this peer relationship between R1 and R2. Okay? And we're going to do it both for IPv4 and for IPv6. All right? Go to the console. So right now we are here on the controller, and I'm going to be using a set of wrappers that I created to invoke the configuration operations on R1. Okay, so I have a set of netconf wrappers that use netconf client that we have here in the controller, which is a small utility that we wrote to send netconf requests or messages to the server, which is the router, and be able to get the responses. And we also have a small gRPC client that is used to send requests to the router and show the responses. So let me just to give you some insight as to what's going on. Let's check, for instance, this wrapper that gets the config. Just so you guys get some. It's a very simple script that basically what it's going to do is print the input of what is being sent, or the message that is sent to the router. This is the actual call to the router where we send in this case, the netconf message, and the script is going to display the response from the router. So that's basically what it does. Okay. So let's start invoking a Git Config. Again, this is a netconf. If you look at the name of the script, all NC scripts invoke netconf transfer. So the first thing that we're going to do is do a Git Config of the OC BGP model. So basically, we're querying for the device. It gives me all the BGP configuration that you have according to the OC BGP model. Okay? So this is the query that we're sending. I don't know how many of you are familiar with the with encoding the RPC model in netconf and with the XML encoding that is used. But basically, we're asking for the running configuration, and we're going to filter. We don't want to get the entire router configuration. We're interested in the OpenConfig BGP model. Okay. So we send the request. This is the we get an empty reply. So basically what the router is saying is, I got your request for the configuration, but there's no BGP configuration right now, so basically it sends empty data. Okay? So no BGP configuration on R1. So what we're going to do next is actually edit the configuration to add the IPv4 peering towards R2. Remember, R2 has been pre-configured to peer back with R1, but R1 has no BGP configuration, as we just verified. So we're going to, using netconf, we're going to put the IPv4 peering configuration in R1 so that session comes up. Okay? So we invoke the script. We see here the input of the configuration. This configuration, let me scroll up a little bit. This is the configuration, the BGP configuration that we're sending to R1 using family of interest. And this is the neighbor configuration. This is the IP address of R2. So we're telling the R1, enable BGP. This is your AS number. Enable the IPv4 address family and peer with R2. Okay. So let's press enter here. The So we sent the configuration, we got an OK. Okay? So let's say we want to verify at this point whether the configuration made it to the router. The Rpc is getting an OK, so everything should have been processed. The configuration should have been processed correctly. Let's verify that. Let's go back to the previous script. If you remember, the very first script that we run returned empty data because there was no BGP configuration. So BGP, the OpenConfig BGP model. So we sent the request. It's going to connect again. In a real-life scenario, you wouldn't be opening and closing this SSH session. You will have a persistent session, but in this case, each script is opening. So we see now that we get the configuration back. Okay? So this is basically a reply to a request for configuration, and we see the configuration that we sent to the router. The AS number, we recognize that we enable IPv4 unicast address family, and we recognize the peering relationship that was, or the neighbor relationship towards R2. Okay? Any questions on this so far? Can people hear me okay?
Yeah.
You guys need to make some noise at some point. Otherwise, I think I'm talking to myself. It feels weird. Okay, so we configure BGP on R1. We were able to verify that the router has the configuration. So what can we do next? If we go again to the diagram, basically we prefixes should have been distributed all the way to R1. So what we can do is actually query the routing table on R1.
Come on, Wi-Fi, you can do it.
Okay. So we ask for the rib, and the rib. Obviously, we don't want to get the entire rib. All the information. There's a vast amount of information that resides in the rib. We're gonna see that we're actually filtering the kind of responsible one from the router, so we get only a subset of the output. Okay. And one thing that you guys should notice is that this command is going to actually exercise an operational data. Okay, so there's something different here. All right, so let's look at the input. This is actually the information that we want to get. We're telling the router. This is using actually the Cisco RIB models because OpenConfig.
I should finish that sentence. The OpenConfig does have a
Well, what happened?
So Santiago, just so you know, when you, it looks like when you use your VM, your audio drops. So you may want to minimize things like bringing up the slides. And when you're pressing enter, there's a couple of seconds here before we hear you again.
Okay, that's fine. So, so this is the input to getting RIB output, and we're asking for prefix and prefix length for IPv4, and we're doing the same for IPv6. We're asking for IPv6 unicast prefixes in the routing table, and we're interested only in prefixes that are BGP, and we want to get the prefix and the prefix length. Okay?
I love XML.
We
50
send the
lines to
request
tell you
for
I don't know any
operational
routes.
data to the router. And we get the response. If we scroll up, we see the prefixes. Okay? So we get the response for IPv4. This is the prefix that R2 is injecting, and this is the prefix that R3 is injecting. Okay? At this point, there are no prefixes for IPv6. Why? We haven't configured any peering relationship yet between R1 and R2. Okay, so R1 reports no IPv6 prefix. Okay? Any questions on this so far?
How does it handle like a commit fail if you fat fingered something in your netconf file?
So netconf supports the same two-stage commit process that you have on the CLI. So actually, when we send the candidate config, you send an RPC call for a commit.
Got it.
Yeah. And you have different options on what to do if the commit fails. The protocol defines those knobs. Okay. All right. So what we're going to do now is switch to gRPC. So gRPC, as you guys probably heard earlier, it's an RPC technology that Google open sourced earlier this year that works over HTTP2, and it has some nice characteristics on terms of performance and flexibility of encoding and flexibility of programming language support. Okay. So I have also a series of gRPC wrapper scripts to exercise the open config. So for this demo, we're going to be using JSON encapsulation for the configuration, and the first thing that I'm going to do is actually ask for the router again, give me your BGP configuration according to the OC BGP model. We should get exactly the same configuration that we have for IPv4, but this time it's going to be formatted in JSON. So we're going to do a Git Config. So basically, we define the operation in the Rpc. This is an Rpc that Cisco has defined based on G Rpc. In G Rpc, you define an IDL with your RPCs. One of the actions that we have defined is a Git Config, and you have to define the name of the model and the path. In this case, it's going to be BGP colon BGP. BGP is the name of the OC BGP model, and BGP is the root of that model. So basically, we're asking for the entire BGP configuration according to the OC BGP model. So we send the request, and we get the response. So let's scroll up. So it's basically the same configuration that we were seeing before. This time, it's a little bit easier to read. JSON is definitely easier on the eyes. So we see the top configuration. We see the AS number 65,000. We see the IPv4 unicast address family has been enabled, and we see the neighbor relationship towards R2. Okay. So let's go now and merge the existing configuration with configuration to bring the IPv6 peering relationship between R1 and R2. Okay, so let me show you the configuration that is going to be sent. The configuration looks very similar. So basically, we're referring to BGP. We're saying for the AS 65001, which is the one that we have configured in R1, we want to enable the IPv6 address family, and this is the neighbor. This is the neighbor address on R2, the peering address that we're going to use on R2. Okay? So we send the configuration. Okay? Next step is to verify. We didn't get an error message, so let's verify that that configuration was actually committed on the router. So we're going to ask again the router for the configuration based on the OC BGP model. So again, we do a Git Config. It's going to be the OC BGP model, and it's going to be the root of the data, the root of the configuration. We send the request, and now we get the reply. And if we look at the reply, we see that now it shows both IPv4, and we successfully merged the IPv6 address family. Right? We see the configuration for the IPv4 peering relationship, and we see the configuration for IPv6 peering. Okay. So we have successfully configured the router. What I'm going to do again at this point is let's check the routing table. Let's see how we're doing with the routing table. Get route BGP. Okay. So again, we're going to send a request for IPv4 prefixes that are BGP. Okay, and we're going to send a request for IPv6 prefixes that are BGP. Okay. Okay, we got the response. Let's look up. Okay, so the first part of the configuration, prefixes according to the IPv4 model. we see the two prefixes. These are the prefixes that were advertised by R3 and R2. This is the IPv4 prefixes. And now we see the data for IPv6, and we see one of the prefixes sticking its head there. And this is the other prefix. Okay? Any questions on this?
So this is all really cool. The XML namespace attribute, I'm assuming all of these models will support, as long as you put that in there, the right namespace, it'll respond with the appropriate model. You don't need to like change the feature. Basically, I want to run OpenConfig now. It'll just do everything. It'll respond in any model as long as you provide the request model, basically.
Correct. Santiago, did you hear the question, or else I'll answer it?
No, I didn't. I didn't.
The answer is yes. If you specify the namespace, you'll get the model that you're looking for.
That was what I was driving at was, do you have to like turn it on and switch modes?
That's a very good question, because actually, for instance, the top of the Cisco Bgp configuration also start with Bgp. Okay, so how would the router know if you send a configuration, that the first XML tag, it's it's a Bgp tag, right? The only way you can know what model the tag is associated with is with the namespace. So you need to specify. That's why at the beginning of both the query and the replies, you get the namespace that is associated with all this data.
Yeah. And then are these scripts published anywhere?
We'll happily post the scripts. I think we'll also do a recording of the demo and post
I have a feeling
too.
of how you're doing it, but it would just be nice to have a place of reference.
Yeah.
So.
Yes.
Can ask,
Okay.
if you do, show commands, do you see the configs being pushed? BGP configs? In a show output? Yeah.
Santiago, the question is, if you just show running config on the box, can you see the config?
Oh. Someone's getting withdrawal symptoms, huh? Okay, that's fine. I'll give you CLI, no problem.
You guys make sure both of your mics are turned on and just leave them on.
Mine is on.
Sure.
The answer to the question is it shows up in the config.
Okay. So what you see here is the CLI configuration. You see that IPv4 and IPv6 address were enabled. You see the neighbor relationship and the policy, the route policy that was configured for IPv4 and for IPv6. Okay. And if we check the routing table, for instance, let's see for IPv4, these are the two prefixes. And if we do it for IPv6, these are the two prefixes we were getting. Okay?
That was come on, this is full citizen to everything else. Bolted onto the side.
I was comparing it to another implementation. So.
Any questions on this before I move to the model-driven APIs?
I think,
APIs.
Santiago, in the interest of time, we're going to stop the demo here because we're pretty much out of time for the session.
Okay.
But if there's any
That's
more
fine.
questions, we're certainly happy to take them.
I've just got a real quick one. It seemed that it was a perception that the G Rpc stuff was responding significantly faster than the netconf XML stuff. Is that a fair statement, or is that just the way the demo was working today?
Santiago, could you explain whether there was any difference in the length of time it took to perform an operation using netconf with gRPC?
The transport is different. In the case of netconf, it's a Python script. That's one difference, right? So the Python is being interpreted. It uses Paramico, which is I don't know if you guys are familiar with that. It's a library, a module, Python module that supports SSH. So the SSH session needs to be established, needs to negotiate, and then the XML needs to be exchanged. In the case of gRPC, it's actually a thin client that we implemented in-house, and it's compiled. It's written in Go, so it's compiled, and also that client just needs to open an HTTP2 session, and actually the data on the wire should go binary using protocol buffer. So I think that's kind of the reason why you see the difference in performance. But you need to take into account, and I mentioned that earlier, that you would establish an SSH tunnel to the router. If you choose to use netconnect, you would establish that, and that is supposed to be a long-lived session. You're supposed to establish that SSH communication channel, and you use it for the duration of I don't know, as long as the box stays up. You're not supposed to be opening these sessions every time you send a message. Does that answer the question?
I guess so. It sounds like it's half because it's compiled code and half because it's actually faster. Or at least the transport is faster, maybe. But maybe the actual response time is no different on the box. I'm not 100% clear on that.
It's hard to hear.
Well,
we can take it offline.
Yeah,
it's fine.
I'll answer the question. I think there's a certain amount of demoitis playing out that makes it look a little slower than it is. There's, as you said, there's some encoding differences, some script versus compiled language differences, but it wouldn't explain the lag that we saw.
Okay.